What is the difference between 2, -2, 2 minus, and 2 plus? That is what we're going to be exploring in today's video about limits. All of us know what 2 is. We all know what -2 is. But what's 2 minus? So 2 minus is 2 minus a little bit. Not enough that we can write out the number. It's like 1.9999999999999 infinitely. It's a fraction less than 2. Following the same logic, 2 plus is 2.000000000 infinite zeros basically. It's a fraction higher than 2. So what's minus 2 minus? Minus 2 minus is a fraction less than minus 2. Minus 2 plus is a fraction greater than minus 2. So minus 2 minus is like minus 2.0000000 something. Minus 2 plus is minus 1.999999999. That is what the difference between these four numbers is. So what does that actually have to do with limits? What even is a limit? A limit, you use a limit, it lets you figure out what the boundaries of a function are. How is it written? Let's say you have a function f of x. This function, f of x, is equal to x plus 2. The limit of f of x, limit f of x, okay, you need to pick a number as x tends towards a number, which we'll put it a, right? So as x is getting close to, let's say that's an a by the way, as x is getting close to 2, what is this? As x is 2 minus, so just a little bit less than 2, what is this? As x is 2 plus, what is this? That is what a limit is. You just plug in what this is. So let's say, for example, limit f of x is equal to the limit x plus 2 as x tends towards, we're going to take the first case, as x tends towards 2. So you plug 2 in place of x, and you get limit is equal to 4. What about the limit as x tends towards 2 minus? Well, as x tends towards 2 minus, that's 2 minus plus 2, which is basically just 2 plus 2 minus a little bit. It's going to be 4 minus. X tending towards 2 plus is going to be 4 plus. Now, the easiest way to understand this properly is through graphs. Let's start. So first of all, we're going to start with this graph right here. One quick thing to note, if you're looking at a graph and you see a circle with a line coming out of it, or I guess a line and then a circle at a point, it means this point isn't actually defined. It's just where it almost reaches. Whereas if you see a point like this, it means that point is specifically defined. Back to this. You've got a line here and a line here, and a dot at x equals 2. Not a dot, sorry, a circle. So first of all, is f of x defined at x equals 2? Is there anywhere on this graph where you see at x equals 2 just a dot, a solid filled in dot? No. All you see are these, which means f of x, let me see. What color should I write this in? Let's do purple. So question 1, no, f of x is not defined at x equals 2. Okay, question 2 part A says limit f of x as x tends towards 2 minus. So remember what we said about 2 minus? It's a fraction less than 2, which means if 2 is right here and it's undefined, you don't have a point there, where is a fraction less than 2 going to be? Is it on this side or is it on this side? It's on this side. So limit f of x as x tends towards minus 2, we need to look at where it is on the y-axis. But so it could either be minus 1 or 2. But we said x tending towards 2 minus, which means we're talking about this line right here, because it's a little bit less than 2. So right here, at 2 minus, the limit is at 2. Okay, limit f of x as x tends towards 2 plus is the same concept, except it's only slightly greater than 2, which in this case is this line. So the limit f of x as x tends towards 2 plus is right here at -1. Okay, so we have that the limit f of x as x tends towards 2 minus is 2, and that the limit of f of x as x tends towards 2 plus is -1. But what about the limit of f of x as x tends towards 2? Does it exist? The way we find that out is we want to check. So we took x equals 2, right? So limit f of x as x tends towards 2 minus has to be equal to limit f of x as x tends towards 2 plus. If this is true, then we can say the limit f of x exists when x tends towards 2. However, -2 and -1 are not equal, so the limit f of x does not, as x tends towards -2, does not exist. Now, we're going to take these 4 questions and apply them to this graph right here. In this graph, you can see that at x equals 2, we have a circle. It's not filled in, which means, let me write it in purple again. 1, no, f of x is not defined at x equals 2 because we have no solid filled in dot. Question 2, limit f of x as x tends towards 2 minus. 2 minus, as we set up here, is on this side of the 2. So we need to find out where that is. And it is right here, which is at 1, 2. So let me write that A, limit f of x as x tends towards 2 minus. We said it's just a fraction behind this, so it's going to be equals to 2. Just check, make sure that's right, yep. And then limit, this is B, limit f of x as x tends towards 2 plus, take a minute, see if you can solve it, is on this side, which is right here, which is also right here at 2. So does the limit f of x as x tends towards 2 exist? Well, is this equal to this? Yes. Limit f of x as x tends towards 2 minus is equal to limit f of x as x tends towards 2 plus, because obviously 2 equals 2. So limit f of x as x tends towards 2 exists at 2. Now, we have one more graph. This one. Obviously, as I'm sure you can tell, the dotted lines are what we call vertical asymptotes, which means the graph is never going to touch those lines. It's never going to hit x equals 2. It's never going to hit x equals -2. So we're going to start with these questions right here. Limit f of x as x tends towards 2 minus. Let's look at this carefully. So if x is a little bit less than 2, first of all, let's locate where 2 is. 2 is right here, right? It's on the asymptote. So 2 minus is a little bit less than 2, which means it's right here. So when x is close to 2 minus, what is the y? So obviously this graph is going to keep going down, 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 down infinitely, and it's going to get a tiny bit closer to 2 minus every single time. It's never quite going to hit it. It's at 2 minus, and it's going down to infinity, which means it's going down to infinity, right? Notice that it's going down minus infinity right here. So the limit of f of x as x tends towards 2 minus, so just a little bit before the 2, is minus infinity. Now, what's the limit of f of x as x tends towards plus infinity? Sorry, as x tends towards 2 plus. X tends towards 2 plus, so we locate the 2 again, it's right here, and plus, which is a tiny bit greater than it. So it's on this side. So as x is right here, what's the y? Again, this is just going up till infinity, so the limit is infinity. Now, what is the limit of f of x as x tends towards -2 minus? So first, let's start by locating -2. It's right here. What's a little bit less than -2? It's going to be to this side. So the limit of f of x as x tends towards minus 2 minus is here. It's gonna be this one, infinity. Okay, so what's the limit of f of x as x tends towards minus 2 plus? Again, locate minus 2 on the graph, and plus is going to be a little bit to this side. So we look at the graph and we can see that a little bit to this side is right here, which just keeps going down, 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 down until negative infinity. Okay, so what's the limit of f of x as x tends towards minus infinity? So when x is at minus infinity, it's all the way over here in this direction. So the limit of f of x as x tends towards minus infinity, we can just take it by looking at this, right? So we've got, let me grab my black pen, just make this a bit more defined. We've got this right here, and x tends towards minus infinity is just slightly above it. This line right here is 0, and x at minus infinity is slightly above that. So we can say the limit of f of x as x tends towards minus infinity is 0 plus a tiny little bit because it never hits it. Now, what about the limit of f of x as x tends towards plus infinity? So plus infinity is all the way over on this side, right? It just keeps getting closer and closer and closer, but it never quite hits it. Again, the line that it almost never quite hit is this line right here, which is 0, y equals 0. But again, so again, it is just slightly above this line, which means it's slightly above 0, which means it's 0 plus. Now, we've discussed how to solve limits graphically, but what about algebraically? How do we solve limits when they look like this? So the first thing you need to know is that we have 4 indeterminate forms. As you're solving limits algebraically, if you get any 4 of these as your answer, you know that you just need to change the method of solving a tiny bit. The indeterminate forms are 0 over 0, infinity over infinity, infinity minus infinity, and infinity minus 0. So we're going to solve these 3, and if we get an indeterminate form in any of them, we know that we just need to change our path a little bit. We're on the right track, we just need to take a slightly different method to get an answer that's not indeterminate. So the first one, our first exercise, is limit x squared minus 4 over x minus 2 as x tends towards 2. So if x tends towards 2, that means that we can replace these x's right here by 2. So let's write that out. Limit of 2 squared minus 4 over 2 minus 2 as x tends towards 2. If we solve that, our answer is going to be 0 over 0, which, as we said, is indeterminate. So what can we do? Well, looking at this, there's one thing that I realize. I notice that x squared minus 4 looks eerily similar to a remarkable identity, a squared minus b squared. So I can take that and I can write limit as x tends towards 2 of x minus 2. Let me close that parentheses and open this one. X plus 2. Divide it all by x minus 2. So now this is solvable. What I can do, I can cross out x minus 2 and x minus 2, and I'm left with x plus 2. And if you plug in 2 to the x plus 2, you're going to get 4, and that is an answer. Now, we've got this one right here. Limit of 2x plus 3 over x plus 1 as x tends towards infinity. So if we were to plug this in, 2 times infinity is infinity, plus 3 is infinity over infinity plus 1. So infinity over infinity, which, as we can see up here, is indeterminate. So we just need to change our track of thinking a little bit. What can we do in this case? Well, because the indeterminate form that we got was infinity over infinity, there's something special that we can do. We can take the highest power over the highest power. The highest power in this case, so the highest power of this term and the highest power of this term. In this case, the highest power is 2x, and in this case, it's x. In other situations, we might get something like x squared plus 4 over x minus 7 or whatever, and then we would take x squared over x. But in this case, our highest powers are 2x and x over 1. So the limit of 2x over x as x tends towards infinity, here we can cross out the x's and we get 2. So the answer to this is 2. Remember, you can only take the highest power over the highest power if the indeterminate form that you got was infinity over infinity, and in some very rare cases, infinity minus infinity. So moving on to the last one. Limit of x minus 4 over radical x or root x minus 2 as x tends towards 4. If we plug this in, I'm sure you know where this is going. 4 minus 4 is 0. Radical 4, root 4 is 2. Minus 2 is 0, which is indeterminate. But this is not infinity over infinity, so we can't take x over root x. What we can do, x minus 4 looks pretty similar. Okay, let me just write this out. Limit as x tends towards 4. Remember, you always need to write this before the answer. So x minus 4 is equal to root x minus 2 times root x plus 2 over root x minus 2. So this, just like this one up here, we can cross out the root x minus 2, and we are left with root x plus 2. So root x plus 2, when x is 4, is 2 plus 2, so the answer is 4. And that is how you solve limits algebraically. Moving on, we've got continuity. What is continuity? We're going to try and figure this out through a series of questions. We're going to start, however, by looking at this graph right here. There's a couple important things to note on this graph. First of all, we have this point, which is not colored in, and this point, which is not colored in, but we've got this point, which is colored in, and this point, which is colored in. This point leads to a line, these two points are connected by lines, and this point is just a standalone point. Our first question, limit f of x as x tends towards 0 minus. Let's go back to limits. Start by locating 0. Where's 0? It's right here. So 0 minus is a little bit less than 0, which means it's on this side. So as x is a little bit less than 0, where do we find a line? Right about here. And this is at this point right here is at 1, 2, 3. So the limit of f of x as x tends towards 0 minus is 3. Now, the limit of f of x as x tends towards 0 plus, we gotta find that. How do we do that? Again, locate 0 on the graph. We've got it right here. 0 plus is gonna be a little bit higher than that, so it's on this side. And where do we have a line with that? Right here. So the limit of f of x as x tends towards 0 plus is also 3, because it's at this line right here, which is 3. Now, does limit f of x as x tends towards 0 exist? Do you think you can solve that on your own? Remember what we said. The limit of f of x as x tends towards 0 exists if this and this are equal. Are they equal? Yes. 3 is equal to 3. So limit f of x as x tends towards 0 exists at 3. Now, is f defined at x equals 0? At x equals 0, which is right along this line right here, is there a point that's defined? Your first instinct, I think, would be to say, no, it's not. Why is that the first instinct? Well, this circle is not colored in, it's just a circle. And I did say that if the circle just is like this, it's not defined. Correct. But remember this little circle right here, the one that's filled in and colored in? That exists on x equals 0. So yes, f is defined at x equals 0 like this. So f of 0 is equal to 0. Why? Should we pause? So, sorry, is f defined at x equals 0? So at x equals 0, we said obviously this point is colored in. So at x equals 0, sorry, I don't think it's 0. 1 second. Sorry, I was wrong about that. My dog startled me. F of 0 is defined. So when x equals 0, y is equal to 1, 2. So f of 0 is defined, right? We have a point that exists at x equals 0. So does f of 0 equal limit f of x as x tends towards 0? So no, these two things right here are not equal. 3 does not equal 0. Or I guess 0 does not equal 3. Right? 0 does not equal 3. Wait, sorry, not 0. I was mistaken with that. So first of all, okay, is f defined at x equals 0? F of 0 exists at this point right here, which is 2. So f of 0 is at 2, not 0. I don't know why I wrote 0. So 3 down here is not equal to 2, correct? So f of 0 does not equal limit f of x as x tends towards 0. Now, is f continuous at x equals 0? No. And why? Because this is not true. F of 0 does not equal to limit f of x as x tends towards 0. Now, okay, so based on this, what is continuity? For f to be continuous at x equals a, which looking at this right here is 0, but it doesn't have to be 0. It could be any number, so we're going to write it down as a. For f to be continuous at x equals a, first of all, the limit of f of x as x tends towards a has to exist. F of a has to be defined. And the limit of f of x as x tends towards a and f of a have to be equal to each other. And that is how to find if something is continuous at a certain point.